Hi all. It's a great pleasure for me to present our paper, Combinatorial Inference on the Optimal Assortment in Multinomial Logic Models. So before beginning with the technical details, I would like to briefly introduce some background on the preliminaries for discrete choice model. So in the year 2000, Daniel McFadden shared the Nobel Prize in economics with James Heckman for his development of theory and method for analyzing discrete choices. So before McFadden's pioneering work, economists tend to predominantly model people's choices as continuous random variables, such as the demand for the varying amount of sugar in daily life. However, in real-world scenarios, there are many situations where it would involve choices that are actually discrete rather than continuous, such as when people are choosing from a collection of distinct options, like selecting the proper costume for a particular event. So in those scenarios, McFadden's work would hold immense significance as it provides the systematic approach for understanding and analyzing discrete choices. So when it comes to choice models, one of the most popular topic is the assortment optimization, which is to provide a mixture of offer products that maximizes the expected revenues. And the ultimate goal is to strike a balance between customer demand and the product revenues so that we can align the offer assortment with the customer decision-making process. And there have been many models proposed in previous works, among which the multinomial logic model will be the one that we will be focusing on in this presentation. So to be more specific, so the multinomial logic model assumes customers to purchase products proportional to latent preference scores. So if we label the products to be from 1 to n and denote by 0 the non-purchase option, then for any given set of offered products, the customer can either choose to buy one atom from the offer set as, or choose not to purchase anything. And we denote the union to be S plus. And under the MNL model, the probability of choosing a particular atom J inside of S plus would be proportional to the latent preference score. So for identifiability, we impose that the latent score for the no purchase option to be 0. And to model the revenues, we associate each product with a revenue parameter. And without loss of generality, we will assume that the products are labeled in descending order based upon their revenues. And the expected revenue would be the expectation of the revenues for the given set of offered products. And the optimal assortment would be the offer set that maximizes such value. So there have been many works proposed on optimization algorithms or estimation of the latent preference scores, such as the one in Bradley Terry Luce model. However, those works are in lack of proper uncertainty quantification, which is actually quite crucial for inferential analysis. And we also know that inferential analysis can be very important in practice because it is in the decision making process. So therefore, in this paper, we try to fill the gap in literature by providing a general combinatorial inference on the optimal assortment S star with uncertainty quantification. So let's look at some concrete examples. So in example 1, one might be interested in inferring whether we should include a particular product I into the offer set to maximize our revenue. And if we look at the, let's take the beverage industry for instance. So the beverage retailer might see some advertisement from TV about a particular brand. Then they might be interested whether it would be wise for them to include this product on shelf to maximize their revenues. And in the second example, for a given category of products and a given ratio Q%, one might be interested in whether we should include more than Q% of the optimal assortment from the category A to get the largest revenue. And going back to the beverage industry example, so the retailer might be interested in whether they should make more than 50% of the products on shelf non-alcoholic or alcoholic to maximize the revenues. So with those concrete examples in place, one might be interested in the question, so why is uncertainty quantification so important? So this is because in practice, the real world data would involve great randomness. So therefore, for the decision-making process, one would need information beyond assortment estimation to quantify our confidence in making such decisions. So if we look at example 1, the diverse sales records might lead the retailers to be more confident in one product, but less in another. So in this case, we need to we need uncertainty quantification to provide the decision makers with a complete picture, so that they can make decisions more wisely. And now we're ready to look at the general framework of our paper. So let's denote by this bullet as the set of all offer sets, and we are interested in this no set denoted by this as no, which is the set of offer sets satisfying certain properties of interest. So we're interested in testing whether the optimal assortment S star belongs to this no set, or say whether this no optimal assortment satisfy some no property of interest or not. However, due to the combinatorial nature of this type of hypothesis testing, we know it can be very challenging in practice to conduct such hypothesis testing. But luckily enough, due to the special properties of the MNL model, actually we can do some reformulation of the original problem to implement the hypothesis testing more easily. So more specifically, under the MNL model, if we define the marginal revenue gap, delta K, to be the difference between the weighted revenues of the top K items and the rest, then it can be observed that the delta Ks are actually non-decreasing with respect to K. And also the optimal assortment would take on this explicit form under MNL, where it would actually be the top K items with the largest revenues, such that the revenue gap delta Ks are still negative. So if we look at the illustration below, so here we have 6 products in total, and the revenue gap delta Ks is increasing with respect to K. However, if we threshold the delta Ks at 0, then actually only the top 3 items will have the revenue gap to be negative. And in this case, the optimal assortment would just be the top 3 items with largest revenues. So from this discussion, we can see that actually inferring on the optimal assortment, S star is equivalent to inferring on its cardinality K star. And by the definition of K star, this is also equivalent to doing this sign change point detection on the revenue gap values delta Ks. So this serves to reduce the original complicated combinatorial inference problem into a simpler one. And now we're ready to discuss our methods. So before we dive into the methodology part, we discuss what is the observed data in this paper. So recall the bolded as is the set of all offer sets. However, in practice, actually it's impossible for us to observe the customer choice outcomes for all combinations of the products. So therefore, to mimic this real-world scenario, we would assume in this paper that we sample the offer set uniformly with probability P, and we only observe the customer choice outcomes for the selected offer sets. And also for the simplicity of presentation, here we assume that the customer choice outcomes sample size would be all equal to L across all selected offer sets, and the outcome would follow the MNL model. Now we're ready for the methodology. So the first step is to obtain a consistent estimator for the latent preference score, and we do so by performing an optimization of the penalized maximum likelihood function. And one may note here that, so it might be noted here that our penalization term is actually a little bit different from the traditional one, where here we actually are penalizing over the sample variance. And we're doing this because previously we imposed this identifiability constraint that makes theta 0 equal to 0. However, if we look at the MNL model, actually all items, including the no purchase option, should be exchangeable. So therefore, we impose this penalty term to avoid ill-conditioned estimator. And this theorem here shows our resulting penalized MLE would actually converge nicely to the truth under proper given conditions. And here we have two highlighted conditions, where the red condition actually is to guarantee that the comparison hypergraph is connected, such that no item would be left out of the comparison. And the second condition is to guarantee that our sample size should be large enough for the comparison, where one may notice that here this condition is with respect to the product of P and L, which shows this exchangeability between the two. And this actually makes sense because the total sample size is actually the aggregated number of customer choice outcomes across all the selected sample set, selected offer sets. So this is actually making sense intuitively. And now, as we know, regularization in the MLE would induce bias in the resulting estimator. So therefore, for the follow-up inferential analysis, we need to first perform some debiasing on the estimator. So we propose in this paper the Newton debiasing with centralization, where we first centralize the penalized MLE by its sample mean, and then we apply Newton debiasing to the centralized estimator. And we argue here that the centralization step is actually essential because due to the identifiability issue, the Hessian matrix is actually singular and perpendicular to the one vector. So therefore, the debiasing term actually only serves to correct arrow in the direction that's perpendicular to the one vector. So we would need this centralization step to eliminate bias in the direction of one. And with the debiased estimator in place, we're now ready for the inferential steps. So recall from previous discussion that we have established equivalence of inferring on S star and inferring on the cardinality K star. So the inference on the optimal assortment can be translated into the inference on its cardinality with the corresponding no set K null. And by definition, this can be further translated into the sign change point detection of the parameters revenue gap delta Ks. So therefore, we can see that the delta Ks here are serving as a pivotal intermediate quantities. And to infer the optimal assortment, we can actually establish a confidence interval for the cardinality K star via some plugin estimators for the revenue gap parameters. And then we can reject the no if and only if the established confidence interval does not overlap with the no set for K star. And as for the plugin estimator for the revenue gap, we can just estimate it by plugging in the previously obtained debiased estimator for the latent preference score. And this theorem here shows that the plugin estimator for the revenue gap are actually asymptotically normal. So this result here is actually sufficient if we are only interested in inferring on a single product, such as in example 1. If I'm interested in only just infer whether we should include a particular product I, whether to include it into the offer set, then 3.4 should be sufficient because we can just utilize the asymptotic normality of delta K hat to infer the sign of delta K. And then we will have some uncertainty quantification for whether to include a product I into the offers optimal offer set. However, when it comes to general inference, this would involve the sign detection for all the products. So therefore, in this case, we would need some uniform error bound on the convergence rate of delta k hat. So therefore, we would define below this maximal statistic, which is the largest standardized convergence error for each delta k hat. And if we can categorize the asymptotic distribution for this t statistic, then we will have a uniform control on the prediction of the sign for each item, and then we can have a valid test for general inference. However, this delta k is actually unknown in practice, so therefore this t is also unknown for observed data. So in order to categorize its asymptotic behaviors, we would approximate t by this Gaussian multiplier bootstrap statistic W, which is obtained by some first-order approximation multiplied by standard Gaussian random variables. And we will compute the, so for any given level alpha, we would compute the quantile of the statistic W conditional on the observed data. And then we can establish a 1 minus alpha level confidence interval for the cardinality K star. And the confidence interval are defined by the formula below. So intuitively, the lower bound for K star would be the K such that the revenue gap is negative enough, and the upper bound would be the K such that the revenue gap is still large enough, such that at both ends of the confidence interval, the revenue gaps would be well separated from zero, so that we will have the sign change point falling in between. And this theorem here shows the validity of our test asymptotically. So under proper scaling conditions, our confidence interval will be valid with the coverage probability bounded below by 1 minus alpha. And in turn, the type 1 error will be well bounded below by alpha, such that our test would be asymptotically valid. So due to time limitation, we will skip the proof sketch for this main theorem. And also we skip the simulation results, but they are in the paper for reference in case the audience is curious. So finally, we conclude the presentation with some possible future directions. So for now, we see that our results are limited to IID data, but in future, we would like to extend the current framework to allow for longitudinal data with adaptive sampling. And also, we would like to generalize in future the current MNL model to more complicated settings, such as we would like to provide general assortment inference for contextual bandit with changing product features. And those generalizations and extensions would require new techniques involving, say, epsilon covering and step-space projection for data dimension reduction. And that's all for my presentation. So thank you very much for your attention.